Acid-base reactions, that's today's topic. Now, what do we already know about acid-base reactions? A fair number of things. One thing we already know is that it's called a neutralization. Now, in a neutralization reaction, as we also already know, we take an acid, react with the base, and we get a salt, and we get water. Now, when a chemist says you get a salt and water, we might mean hydrochloric acid reacts with sodium hydroxide to make sodium chloride, table salt, and water. But really, when a chemist says salt, he means any ionic compound that is the result of an acid-base reaction. And by extension, you could say the word salt for any ionic compound. So in an acid-base reaction, we get water, which is a molecular, covalent bonds, and we get an ionic compound, and we call the ionic compound the salt.
That was easy.
It's almost always that easy. There's two things that will complicate it. Number one, when we say neutralization, we mean the reaction between an acid and a base. We mean the complete reaction of an acid and a base. The problem is, it won't necessarily result in a neutral solution. Not something we're going to have to worry about, though, but just so you know, neutralization is the name of the reaction, not the result. Not the resulting solution, I should say. And the other thing is, if I have a weak base, and we generally don't deal with weak bases in this course, but if I have a weak base, then it could get a little bit smaller. Okay, so instead of a double displacement type reaction, I now have more of a synthesis type reaction. Here I've got ammonia, which is a weak base. Now if you look at that, you say, well, where's the hydroxide? That's actually the problem with it. Reacting with hydrochloric acid to produce ammonium chloride. Now it is ionic. There's my ammonium ion, there's my chloride ion, so I do have an ionic compound, so it is salt, but there's no water. Now again, for us, we generally deal with strong bases, so that's not really going to be an issue for us. To do a neutralization, and we're going to do several, we call it a titration. We'll set it up as a lab, we'll prep it as a lab, you'll learn the skills, but in order for us to do a titration, we're going to need to know volumes. Both volumes. Now those are things that we can measure, so that's pretty easy. And we'll need to know the concentration of one of them, either the acid or the base, and then we use that information to figure out the other. Neutralization, equal numbers of moles of acid reacting with numbers of moles of base. So we set them equal to each other. And since I'm talking about solutions, I've got a molarity and a volume situation going on. So it looks like a familiar formula. We're going to tweak it a little bit to make it work for a neutralization. The equipment you use, the setup you'll have, is something that looks a bit like this. So we have a couple pieces of equipment that are very unique to working with solutions and very unique to doing titrations, which we haven't seen yet, but we will again in a couple of days. So let's talk about a partial neutralization. Now, if a true neutralization is the complete reaction between an acid and a base, then a partial neutralization is when you have not enough acid or not enough base. And the result, of course, is not a full neutralization, but you have a little bit of excess. So it's kind of like a limiting reagent question, except we don't care about the limiting reagent this time. We want to know which one is in excess, because the excess one controls the pH. So you got this question down? If not, pause it while you do, and then I'm going to keep going with it. So there's the reaction, and just so you know, we're always going to do these kinds of questions with 1 mole of acid reacts with 1 mole of base to produce stuff. But again, really all I care about right now is the reactant side. Here's what we know so far. We know the molarities of both, we know the volumes of both. Now what we're going to do is we're going to zoom in on the reactant side because it's the excess reactant that's going to control the pH. You'll notice over here there's nothing about this salt or the water that says acid base, anything about pH. So it's all going to be about the leftover reactant. So zooming in, repeating some stuff that we already know, the molarity of the acid, volume of the acid. I'm going to use that to calculate the numbers of moles of acid, molarity times volume. And out of that, I get decimal 0.125 moles of acid. Now, I want to caution you here right now. If you love rounding numbers off, please don't. Carry the extra decimal places. It'll make a big difference later on because we're going to end up with questions where the numbers of moles are fairly close. And if you round off, you'll think they're exactly the same, and they're not. I'm going to do the same thing for the base. I know my molarity. I know my volume. I calculate numbers of moles, and I get decimal 0.1225 moles. So I need to be careful because at first glance those two things look a lot alike, and they're not. And that very tiny difference down here in the fourth decimal place, that's going to make all the difference. I said excess reagent controls the pH, so which one is excess and how much excess is there? Well, the excess, and if you say that to yourself fast a couple times, you'll see where I get those letters from, is the larger one minus the smaller one. Now, in this case, I had more acid. See? More acid. But I take the larger one and I subtract the smaller one. Doesn't matter if it's acid minus base or base minus acid. Big one minus little one. And in this case, I get that many moles. Now, again, if you were rounding things off, you'd get something different, and this is where we need to carry a few extra decimal places because a tiny difference is going to make a lot of difference. Number of moles of acid then is decimal 0.025 moles. Now, your calculator, mine did, yours might have given you 2.5 times 10 to the exponent negative 4. And it might have written it a little bit different than that, but this is what it did. It went in scientific notation. That's okay. Your calculator knows what you're doing. Hopefully you know what you're doing, and we'll get in the same place. Now, if I'm trying to find pH, I need to have a concentration. So not numbers of moles, concentration. This is the biggest mistake that I see is people use this number, the numbers of moles. They'll use that in their pH calculation. I have to have a concentration, moles per liter. So combine my volumes. Remember, I had 25 mils and then I had 24.5 milliliters. So combine those. It's got to be in liters. Combine them and then find my concentration. Clean that up. There's my new concentration. Now again, if I like rounding off, I've got a slightly different number here. It'll end up showing up quite large in the final number. So there's my new concentration. That is the concentration of excess leftover acid that didn't react with base. That is going to have a role in the pH. It's going to control the pH. So find the pH. pH is the negative log of that hydronium ion concentration, which means negative log of that number, which means that. And after telling you don't round off, don't round out, don't round off, I rounded off a little bit. But now I've rounded off at my final answer rather than all the way through. Okay, let's try another one like that. But here's the big plan. So if you want the overall plan, and this is true for everything, you're going to calculate numbers of moles. You're going to calculate the numbers of moles of excess reagent. 2 lines to say that. Calculate the excess reagent. Calculate the molarity, and then figure out the pH. Now we know 2 ways of finding pH. We know how to find the pH of an acid. We know how to find the pH of a base. Slightly different. Make sure you know which one it is you're working with. Here's the question. 175 milliliters of 0.063 mole per liter acid mixed with 25 milliliters of 0.45 moles per liter of base. Same job. Calculate the number of moles of each, calculate the excess, calculate the concentration, calculate the pH. Number of moles of acid is the concentration of the acid times the volume of the acid. And again, don't round off. I know it's awfully tempting to do so, and wow, I don't want to carry around 6 decimal places, but just do it for the first couple and see where you end up. Calculate number of moles of base. Same thing. Okay, so I've got 1, 2, 3, 4, 5 decimal places. 1, 2, 3, 4, 5, 6. But if you see, it's not a huge difference, right? And maybe it's the numbers I picked, but they're going to end up being close all the time. So you need those extra decimal places. This number, the number of moles of base, was a little bit bigger, so I subtract the acid from the base. So big number minus little number. If you can't tell, do the subtraction. If you end up with a negative number, switch it around. Now I'm way down here into my 6 decimal places again. There's my final numbers of moles of base, but that's not what I want. I want the concentration. So I divide that by the combined volume. So 175 milliliters with 25 milliliters gives me 200 milliliters. 200 milliliters, 0.2 liters. My new concentration is here, which is odd because it's, and I didn't notice that before. And then you use that, and clean it up a little, to find the POH. Remember, it's a base, so POH, and then find the pH is 11.5. So it's a lot of work, a lot of steps. It's not that hard to do, but we do need to keep track of a lot of things. Sorry if I was doing this and you thought I meant something else. It's just keeping track of all kinds of stuff. Here's one for you to try. Same kind of deal, same plan. I don't know from looking at it which one is in excess. That's kind of intentional. It would be more helpful if it was the excess base, because then that forces you to do an extra step, but we'll find out. And that's about all there is to it. So hopefully this makes sense. Hopefully this question works, and we'll talk to you later in class. See you.